Okay, class, welcome to lecture 9. Today we're talking about expected value and standard deviation. So last time we ended on expected value, did I think like one example of it. So now we'll go into more detail and then also talk about standard deviation, which is a phrase, a term we've seen before, but now we're going to apply it to something else, to probability distributions. Okay, so just to remind you, expected value, the name, the way you should think about is that it's, sorry, let me phrase this better. The name comes from being the value you expect, there you go, there are the words, to get if you do the experiment many times. So that's going to be the idea that you should think about. And the mean is really the same thing, but for data. And the way we can think about it, in the last example I did in the previous video, we had these data points 2, 4, 6, 6, 4, 4, 2, 3, 5, and 5. The idea is like if I had a bag with these numbers in them, and I went and I grabbed one randomly, and I did that a bunch of times, then the mean is the same as the expected value, and it's going to turn out to be the average of what I would get if I did this experiment a bunch of times. Okay, so this is how to think about it. Let's do another example though to remind ourselves about how it works. So let's calculate the probability, sorry, the expected value for a probability distribution, which remember is just some chart with little x's on one side, and then the probability of that little x happening on the right side next to it. So in this experiment, we have that our little x could be 0, 1, 2, or 3. And our probabilities, I'll use decimals this time instead of fractions, 0.01, aka 1%, 10%, 0.10, 38%, and 51%. So that should add up to 100% to be good, right? Okay, so let's calculate this expected value and then think about it in the above way again. So it's 0 times, because I multiply the x with the probability of it happening. So I do 0 times 0.01 plus 1 times 0.10 plus 2 times 0.38 plus 3 times 0.51. So you can add all this up and you'll end up with 2.4. And so the way you interpret this, because I don't have data, I have a probability distribution, but you interpret this as sort of something like this. We expect to get an average or a mean of 2.4. Oops, can't write today. 2.4. If we like randomly picked 0, 1, 2, or 3 according to these probabilities. So like you can picture this with a bag, which I'll do in a second. We select 0, 1, 2, 3 according to these probabilities. So one way to picture this is like if I had a bag of 100 numbers, and I made one of them be a 0, because only 1% of them are zeros, and I made 10 of them be 1s, I'm not going to do the rest, but I had a whole bunch of 2s. I had 38 2s and 51 3s. If I had a bag and I mixed them all up here and I randomly picked one, but then I did that or repeated that experiment, I put the number back in, I did it again a bunch of times, then I calculated the average of all the numbers I picked, we would expect it to be around 2.4. Of course, it doesn't have to be, but most likely it will be near 2.4, and the more we do it, the more likely it is that it'll be near 2.4. Okay, so that's the intuitive understanding of expected value, and that's how it's related to the mean or an average. So that's interesting because it leads to something else. So expected value is just like the mean, but for probability distributions. So what's something we learned about that goes with the mean sort of is the standard deviation. So let's see if there's an analogous concept for standard deviation. And how would that work? Okay, so I guess I just need to jump into an example to try to make it work. So what I'll do is I'll start with a probability distribution, just some that might look a little familiar from last time. Actually, no, sorry, this is the new one I just made up. Okay, so I'll do 1, 2, 3, and 4. My probabilities will be 2/8, 1/8, 1/8, and 4/8. So then we know how to calculate expected value. So let's do that first, because if you're calculating the mean or if you're calculating the standard deviation using a bunch of data, what's the first step to doing that is you need the mean. So I'm gonna get the expected value since it corresponds to the mean, and that should help me get the standard deviation. Okay, so you know how to do this now. Okay, so 1, 2, 3, and 4. Multiplied by each of their probabilities and then add it up. So if you add all this up, you'll get, let's see, 2 plus 2 plus 3 plus 16 over 8 is 23 over 8. Good. Okay, so that's my mean or my expected value. So if this is like the mean, what should I do next? Let's see. To get the standard deviation. We should subtract, but so when you calculate the standard deviation for data, you take your mean and you find how far away it is from each data point. You subtract from each data point. But now I don't have data points. Instead, I have possible values of my random variable, little x's. So that's what I'm going to subtract instead. So I'm going to do each little x minus the expected value. And then what did we do for standard deviation after that? We squared to make them positive. But then we're going to do something a little bit different after that. Okay, so let's get going though. So instead of my data points, subtracting my mean, it's going to be my possible values of the random variable minus the expected value. So it's going to be doing this. Okay. So if you just calculate these fractions, you get negative 15/8, negative 7/8, 1/8, and 9/8. Okay. And then I'm going to square each one, because that's what I did for standard deviation when I was calculating it for data. So it's kind of annoying, but we can do it because we have calculators. So I already did these ahead of time, so I'm just copying them down. Okay, so that's what happens when I square them. Remember, the reason you square is to get rid of the negative. Okay, and now is a different step than the other one. So here, what we have to do is we have to account for the probability somehow. So the idea is that this 3 is showing up 1/8 of the time if it were a bunch of data. So I sort of have to think about it as when I subtract my 3 minus my mean, I have to do this 1/8 of the time, because if it was a bunch of data, that's how many times I would do it. And my 1 would be this would be subtracted 2/8 of the time. So how can I incorporate that? Well, I can just multiply that difference, that distance, by the ratio that it shows up. So that's what I would do. So that's what we're going to do here. Okay, so I'm going to multiply by the corresponding probability for that data point, for that possible value of little x. So this one I'm going to multiply by 2/8 because it came from the 1, which had a probability of 2/8 associated to it, and so on like that. So the next one will get a 1/8, then another 1/8, and then this one will get a 4/8. Okay. So this is the multiplication we have to do. And then, so I'll do that for you because I did it ahead of time, so you don't have to try to do that. But you would use a calculator or something. If you wanted to check this, you'll get this. Okay. And now, what did we do next for standard deviation? This was sort of like after squaring and doing it for each data point. That's what multiplying by the probability is doing. It's sort of accounting for the fact that instead of having data points, we have probabilities. So now what we do is we add them all up. That's what we did next in the standard deviation. So we add these up. I'm just going to skip that. That takes forever. So just take it's 924 over 512. If you check that. And this would sort of be like the variance. So how do I get the standard deviation? After I add everything up, I have to square root that. So then this thing is the standard deviation. And if you plug that into a calculator, it's going to be around 1.34. Okay, so that's the idea. Let me just one more time explain why I'm multiplying these by probabilities in a different way. So the probability is multiplied. So each of these distances from the expected value is weighed proportionally to how often it would appear. If it came from data. That's the idea. We don't have any data. What we have is probability. And so we don't have data points. We have these little x's. And the probabilities tell us how often they would appear if we were to like grab a bag full of these numbers according to these probabilities. So these distances are also going to appear that often. So we have to multiply the distances, these distances here, after squaring, I guess, by the probability to get the distances to correspond. Okay. So now let's just check that everything works out. So how can we do that? Well, we can do this with data and make sure that we get the same answer twice. So that'll check that everything is working out. So for example, if I give you this data, I'll just do a very small example, 2, 4, 4, 5, 6, and 6. If I calculate the standard deviation in both ways, I should get the same answer. So first, I can turn this into a probability distribution. We learned how to do that last time. So the way that works is on the left, you put the possible values of little x, and that just comes from the possible data points. So here the data points can be 2, 4, 5, or 6. And then the probabilities you put on the right are just how often they show up. So 2 shows up 1 out of 1, 2, 3, 4, 5, 6 times. 4 shows up twice out of 6 times. 5 shows up once out of 6 times. And 6 shows up 2 out of 6 times. So now you could use this to calculate the mean and standard deviation, or you could use the data. 2 different ways. Okay, so let's do that. Old way. So I'm just going to speed it up a bit because you don't want to watch me do a million calculations. But if you do it, you'll calculate that the mean is 4.5. And then you do all these things. So you do each data point. So you got to do all the data points subtracted. So I'll do it here, I guess. Five minus 4.5 is 0.5. 6 minus 5. Got to do that twice. And so what's going on here is I'm using all the data. So then I have to square everything. So I'll get 6.25. So now the negatives will be gone, 0.25, 0.25, 0.25, 2.25, 2.25. Then you add these up and divide by 6, because there are 6 of them. If you do that, you'll end up with 1.92. So notice in the other method, I didn't have to divide by anything. I just added. That's because the probability was taking care of the division. Okay, so we'll see how that corresponds when we get to that example for this one. All right, so then that's the variance. So the standard deviation, we know, is the square root of that. Okay, so that's the old way. So then the new way, we'll make sure we get the same thing. Just to make sure everything works. I get the expected value, which I'll leave it to you to calculate. It's 4.5 again, because it's the same as the mean, but it'll work out if you do it the long way. And then I do subtraction, but not for each data point, but for each possible value of little x. Oops, I skipped 2. So there's just 2, there's 4, there's 5, and there's 6. And instead of doing them as often as their data appears, I'm going to bring that in by using probability after. So if I do these, I get negative 2.5, negative 0.5, 0.5, and 1.5. Then I'm going to square these. And so you can already sort of see the correspondence. If I zoom out here, these are the same as these, except on the new method, each thing is only appearing once for each time it's done. for each possible value that you could have. But on the old way, it's done every time the data point shows up. Okay, so then instead of adding at this point, we multiply by the probability. And that is what is going to account for the fact that some data shows up more often than others. So this first guy, I'm going to multiply by 1/6. And then the next one I'll multiply by 2/6, and then the next one by 1/6, and then the last one by 2/6. So this is what I'm doing, except I zoomed out, so now it looks all weird, but it's okay. Okay, so I'm multiplying. Oops. Okay, and then I'm going to add those up. And that will, again, be 1.92. And then standard deviation will be the square root of that. And voila, that's exactly what we wanted. Good. Okay, so that's it for this lecture. See you next time.